Welcome to Softly Curious. Find a comfortable position, let your breathing slow, and allow the next few hours to pass gently. The subject is ice, one of the most familiar things on Earth and one of the least understood. It sits in your glass, forms on your window in winter, covers entire continents, and drifts through the outer solar system. Most people encounter it every day without once wondering what it actually is. The more carefully you look at ice, the stranger it becomes. It does not behave the way most substances do. It does not follow the rules that govern metals, rocks, or most liquids when they cool and solidify. Ice is an exception, and that exception has shaped the surface of this planet more than almost anything else in its history. Most solids are denser than their liquid forms. When something freezes, its molecules slow and pack tightly together, making the solid heavier than the liquid. Water does the opposite. Ice is less dense than liquid water, which is why it floats. This is not a minor detail. It is one of the most consequential facts in the history of life on Earth. When a lake freezes in winter, ice forms at the surface and stays there. It acts as insulation, trapping heat in the water below and keeping it liquid through the coldest months. Fish, plants, and microorganisms survive beneath that frozen ceiling. If ice sank like most solids, lakes would freeze from the bottom up, layer by layer, and almost nothing living in them would survive a serious winter. The reason water behaves this way is molecular. A single water molecule, two hydrogen atoms bonded to one oxygen atom, carries a slight electrical imbalance. The oxygen end is weakly negative, the hydrogen end's weakly positive. This causes molecules to attract one another in a specific orientation, forming connections called hydrogen bonds. In liquid water, these bonds break and reform constantly, millions of times per second. When temperature drops far enough, that constant motion slows. The hydrogen bonds stop breaking and lock permanently into place, forming a hexagonal lattice, a six-sided, open, repeating structure. This arrangement holds molecules slightly further apart than they were in liquid form. That is the source of the expansion. Ice takes up more space than the water it came from, which is why a sealed bottle left in a freezer will eventually crack. Ice is slippery, and the explanation most people have heard is not entirely accurate. The common idea is that a skate blade melts the surface through pressure, creating a lubricating film. But calculations show that the pressure a blade actually exerts is far too low to melt ice on its own. The real explanation involves something called a quasi-liquid layer, a thin film of molecules on the surface of ice that never fully solidifies. Surface molecules have fewer neighbors to bond with than molecules deeper inside the crystal. This leaves them in a semi-mobile state, loosely organized, never completely locked. The quasi-liquid layer exists on every ice surface at all times, independent of any contact or pressure. It is thickest near 0 degrees Celsius and thins steadily as temperature drops. Very cold ice near -30 or 40 degrees is noticeably less slippery because that layer has become too thin to function as lubrication. This temperature dependence is why ice rinks are maintained so carefully near zero. Too cold and skaters lose their glide. The surface needs that mobile layer to perform. What feels like a simple frozen surface is actually a precisely engineered physical state, held at the exact temperature where molecular instability becomes useful. Ice is not a single substance. Scientists have identified at least 19 structurally distinct forms, each stable under different combinations of pressure and temperature. The ice in a glass or a snowfield is ice. The hexagonal form, stable at normal atmospheric pressure. Compress water beyond that, and the molecules are forced into tighter, more complex arrangements with entirely different densities and properties. Ice 6 forms under pressures found in the deep ocean. Ice 7 forms under pressures roughly 10,000 times greater than atmospheric and remains solid even above 100 degrees Celsius. Boiling temperature means nothing to ice 7 pressure overrides it completely. These forms are believed to exist inside the mantles of large icy moons scattered across the solar system. Color is the last thing most people associate with ice, yet ice has one. In a glass, it appears clear. In a glacier, it turns blue. Compressed ice absorbs red and orange wavelengths of light more efficiently than blue ones. As light travels through many meters of dense, ancient ice, the red spectrum is gradually filtered out, and what remains is blue, not a reflection, but the actual optical character of the material itself. The oldest glaciers, compressed over thousands of years until nearly every air bubble has been pressed out, glow the most intensely. The denser and older the ice, the longer light must travel through it, and the more complete the filtering becomes. That striking color visible inside Antarctic crevasses or along the face of a Greenlandic glacier is not a reflection of the sky. It is the true color of ice, revealed only when there is enough of it to show what it has always been. Every snowflake begins as a single dust particle suspended in a cloud. A water molecule attaches to it, then another, each locking into position according to the same hexagonal rules that govern all ice crystals. The six-sided symmetry of a snowflake is not decorative. It is a direct consequence of molecular geometry established the moment the first hydrogen bonds form. The hexagon is the only shape water molecules can build when they crystallize under standard atmospheric pressure. As the crystal grows, each of its 6 arms extends into the same environment, the same temperature, the same humidity, the same pressure. Because all 6 arms experience identical conditions at the same moment, they grow identically. The branching that appears on one arm appears on all 6 simultaneously. The result is near-perfect 6-fold symmetry, not because anything is directing it, but because the same physics applies equally in all directions at once. No 2 snowflakes are the same. This is a statistical reality, not a poetic one. As a flake falls, it passes through layers of slightly different temperature and humidity, and each shift alters the rate and pattern of crystal growth. Over a descent of several hundred meters, the exact sequence of conditions any single flake encounters is unique. The number of possible growth paths is so large that 2 flakes following identical ones is, for all practical purposes, impossible. Wilson Bentley, a farmer from Vermont, spent nearly 50 years photographing individual snowflakes through a microscope beginning in 1885. He captured more than 5,000 images before his death and never found 2 that matched. Science confirmed what his photographs suggested, that the space of possible snowflake structures exceeds the number of atoms in the observable universe. Every flake that has ever fallen has been, in the deepest structural sense, entirely its own. Not all snow crystals are the elaborate branching stars most people picture. Temperature and humidity at the moment of formation determine shape. Very cold, dry air produces simple hexagonal plates or columns, compact, almost geometric, with none of the elaborate branching of warmer conditions. The intricate stellar dendrites that appear on winter windows form only within a narrow band of temperature, just below zero, where growth is fast enough to send arms branching outward in all directions. Ice makes sound. The crack of a frozen lake underfoot, the tick of ice cubes dropped into a warm glass, the deep groan of a glacier in the dark. These sounds have distinct physical causes. When ice cubes crack in a drink, warm liquid heats the outer surface while the interior stays cold. The outer layer expands faster than the core can accommodate, and the stress releases suddenly as a fracture. The sharp sound is the crack traveling through the crystal. Glaciers produce something entirely different. As a glacier moves, and all glaciers move, some faster than a meter per day, the ice deforms under its own weight. Sections slide, compress, and fracture at depth. The sounds range from low rumbles to sharp reports, carrying across entire valleys. Frozen lakes in deep winter boom and groan as temperatures fall and the ice sheet contracts. These are not signs of failure. They are ice adjusting to pressure, finding equilibrium. Water does not always freeze at 0 degrees Celsius. Under certain conditions, it can remain liquid well below that, a state called supercooling. For freezing to begin, water molecules need a surface to crystallize around, called a nucleation site. This can be a dust particle, a mineral grain, or a microscopic imperfection in a container wall. In the complete absence of any such site, pure water in a smooth container can remain liquid down to around -40 degrees. Supercooled water is metastable. It exists in a state physics would prefer to resolve, but cannot without a trigger. Introduce a single ice crystal or a sharp vibration, and the entire volume can freeze almost instantaneously. Supercooled droplets are common in high-altitude clouds, where temperatures fall well below zero, but nucleating particles are scarce. Aircraft icing occurs when these droplets strike a cold surface and freeze on contact, sometimes within fractions of a second. The 22 degrees is not arbitrary. It is the minimum angle at which light can exit a hexagonal ice prism, so more light accumulates there than anywhere else, producing a bright ring with a darker interior. Sun dogs, two luminous spots flanking the sun near the horizon, form when plate-shaped crystals drift horizontally and refract light sideways. Circumzenithal arcs, light pillars, fire rainbows, all of them are the geometry of the hexagonal lattice written across the sky. Dry ice is frozen carbon dioxide. It shares almost nothing with water ice beyond the word frozen. Water ice forms at 0 degrees Celsius at standard pressure. Dry ice forms at -78.5 degrees and does not melt. It sublimates, moving directly from solid to gas without becoming liquid. There is no puddle, no wet surface, nothing left behind. The carbon dioxide returns to the air, and the fog that appears around it is something else entirely. That fog is water vapor in the surrounding air, condensed into droplets by the extreme cold of the sublimating surface. Dry ice is far colder than water ice, making it essential for transporting vaccines and biological samples where conventional ice cannot hold a low enough temperature. Touching it directly causes immediate frostbite, not from wetness, but from the rate at which heat is pulled away from skin. The fundamental difference between the two is molecular. Water ice is held together by hydrogen bonds, strong, directional, costly to break. Dry ice is held by much weaker forces between carbon dioxide molecules, which release easily at mild temperatures. This is why dry ice vanishes within hours at room temperature, while water ice persists through a cold morning. The staying power of water ice comes down to the quiet and unusual strength of the hydrogen bond. There is a difference in how water ice and dry ice behave in the air around them. Water ice melts gradually, releasing moisture as it goes. The air near melting ice becomes cold and damp. Humidity rises, surfaces condensate, and the chill spreads slowly outward. This is the cold most people know from experience. Wet, lingering, seeping into a room or a container over hours. The temperature drops, but the air stays full of water. Dry ice works in the opposite direction. As it sublimates, it displaces the surrounding air with carbon dioxide gas and pulls heat away so rapidly that any moisture nearby condenses or is driven off. The air around dry ice becomes intensely cold and dry at the same time. There is no dripping, no pooling, no gradual release. The cold arrives all at once and leaves nothing behind when the dry ice is gone. In practice, this distinction determines where each one is used. Water ice cools drinks, preserves fish, and lines the bottom of coolers where moisture is acceptable or even welcome. Dry ice ships organs, vaccines, and compounds that cannot tolerate any liquid contamination. Theatrical fog machines rely on dry ice because the effect vanishes cleanly without soaking the stage. Each is frozen, each is cold, but they belong to different chemical worlds, and the boundary between them is absolute. Ice ages are not rare events in the history of this planet. Earth has passed through at least 5 major glacial periods over the last 2.5 billion years, each lasting millions of years and reshaping the surface of the continents. The most recent, the Quaternary glaciation, began around 2.5 million years ago and, in geological terms, has not fully ended. The ice sheets covering Greenland and Antarctica are remnants of it. Within each major glacial period, the climate oscillates. Ice advances and retreats in cycles driven by small but consistent changes in how Earth moves around the Sun. During the most recent glacial period alone, there were more than 20 distinct glacial advances, separated by warmer intervals called interglacials. The last glacial maximum ended roughly 20,000 years ago. The warmth that followed is the climate in which all of recorded human history has taken place. Before any of these recent cycles, there was something far more extreme. Around 700 million years ago, evidence suggests that Earth froze almost entirely, a hypothesis known as snowball Earth. The oceans may have been covered by ice hundreds of meters thick, from the poles to the equator. Temperatures dropped globally to around -50 degrees Celsius. The mechanism was a runaway feedback. As ice spread, it reflected more sunlight back into space, cooling the planet further. What ended snowball Earth was not warmth from the sun, but carbon dioxide from volcanoes. Beneath the ice, volcanic activity continued uninterrupted. With the oceans sealed, carbon dioxide accumulated in the atmosphere for millions of years until the greenhouse effect became strong enough to melt the ice. The evidence survives in ancient rock formations on every continent, glacial deposits sitting directly beneath tropical limestone, 2 climates compressed into a single layer of stone. The more recent ice ages follow a rhythm identified by a Serbian mathematician named Milutin Milankovic in the early 20th century. He described 3 cycles in the geometry of Earth's orbit that together influence how solar energy is distributed across the planet. The first is the shape of the orbit, stretching from nearly circular to slightly elliptical over roughly 100,000 years. The second is the tilt of the axis, which varies over a cycle of 41,000 years. The third cycle is precession, a slow wobble in the direction Earth's axis points, completing a full rotation over 26,000 years. None of these cycles significantly alters the total solar energy Earth receives. What they change is its distribution across seasons and hemispheres. When northern hemisphere summers become slightly cooler, winter snow and ice survive into the following year. Layer by layer, century by century, those survivals accumulate into continental ice sheets. Glaciers move. This is not obvious from looking at one, but a glacier is always in motion, pulled downhill by gravity at rates ranging from a few centimeters to several meters per day. The ice at the base is under enormous pressure, which lowers its melting point slightly and allows a thin film of meltwater to form. The glacier slides on this film. Ice crystals within the mass also deform plastically under pressure, allowing flow even where no meltwater exists. As a glacier moves, rocks embedded at its base grind against the bedrock below, wearing it down over thousands of years. The resulting sediment gives glacial meltwater its characteristic gray-green color. Larger rocks are plucked from the bed and carried hundreds of kilometers before being deposited when the ice melts. These displaced boulders, called erratics, sit in landscapes with no geological relation to the rock beneath them, carried there by ice and left behind. Fjords are among the most dramatic evidence of what glaciers leave behind. A fjord forms when a glacier carves a valley deep below sea level, then retreats as climate warms and the ocean floods in. The shape, steep walls dropping into dark, still water, is the direct imprint of glacial erosion. Norway's Sogne Fjord reaches depths of over 1,200 meters. Greenland's Scoresby Sound stretches more than 350 kilometers inland. Both are the work of ice. The valleys between fjords carry the same signature. U-shaped cross-sections, flat bottoms, and near-vertical walls distinguish glacial carving from the V-shaped profiles cut by rivers. In mountain ranges across the world, the Alps, the Rockies, the Southern Alps of New Zealand, these forms record glaciers that vanished thousands of years ago. The ice is gone, but the geometry it imposed on the land holds the outline of a climate that has not returned. Where glaciers retreated slowly, they also built. Debris carried within the ice was deposited at the glacier's edge as it melted, forming long ridges called moraines. Terminal moraines mark the farthest point a glacier reached before retreating. Some of the most fertile soils in North America and Northern Europe were built from glacial sediment deposited during the last glacial maximum. Ground rock spread across landscapes by ice that has been gone for 10,000 years. The Great Lakes of North America owe their existence to the same process. As the last ice sheet retreated, its weight had depressed the bedrock beneath it. Meltwater pooled in the basins left behind, and the land began slowly rising, a process called isostatic rebound that continues today in parts of Scandinavia and Canada, where the ground is still rising at rates measurable with modern instruments. The ice departed, but the land is still recovering from the weight of it. The scale of the last glacial maximum is difficult to hold in mind. Ice sheets across North America and Eurasia reached thicknesses of 3 to 4 kilometers in places. So much water was locked in ice that global sea levels were roughly 120 meters lower than they are today. Land bridges appeared between continents now separated by open ocean. Britain was connected to mainland Europe. Alaska and Siberia were joined by a wide corridor of dry land. Humans crossed that corridor. The peopling of the Americas almost certainly passed through the Bering Land Bridge during the last glacial maximum, when sea levels were low enough to expose it. The Ice Age did not simply shape the landscape. It shaped the routes by which our species spread across the planet. The geography of that frozen world determined where people could go, and in doing so, determined where they eventually settled. The melting that followed the last glacial maximum was not a smooth process. It happened in pulses, interrupted by cold reversals lasting centuries. One of the most dramatic was the Younger Dryas, a sudden return to near glacial conditions that lasted roughly 1,200 years before ending almost as abruptly as it began. The most widely accepted explanation involves a disruption of ocean circulation triggered by a sudden release of cold meltwater into the North Atlantic. Buried inside the ice sheets of Antarctica and Greenland is one of the most detailed archives of Earth's climate that exists. Scientists access it by drilling cores, long cylinders of ice extracted from depths that can reach 3 kilometers or more. Each core is a vertical record of snowfall, compressed over hundreds of thousands of years. And reading it is like turning the pages of a book that the atmosphere wrote without knowing anyone would one day read it. The most valuable contents of an ice core are not the ice itself, but the tiny bubbles trapped within it. As snow falls and accumulates, it traps air between its crystals. Over time, as the snow is compressed into ice under the weight of new layers above, those pockets of air are sealed permanently. The bubbles that survive in deep ice cores contain actual samples of ancient atmosphere, air from a world that existed before humans, before agriculture, before recorded history. The oldest continuous record comes from Antarctica. The Epica Dome Sea Core, completed in 2004, extends back approximately 800,000 years. Within that span, the record shows 8 complete glacial cycles, 8 advances and retreats of global ice, each lasting roughly 100,000 years. The pattern matches the Milankovitch cycles with a precision that transformed theoretical orbital predictions into directly observable fact preserved in frozen form. What the bubbles reveal is striking. Carbon dioxide levels in the ancient atmosphere rose and fell in close alignment with temperature shifts recorded in the ice itself. During glacial periods, atmospheric carbon dioxide dropped to around 180 parts per million. During warm interglacials, it rose to around 280. For 800,000 years, it never exceeded 300 parts per million. Current levels are above 420. The air in those bubbles is not the only information a core carries. The ice itself records temperature. Water molecules containing slightly heavier oxygen isotopes condense and fall as snow at different rates, depending on temperature, which means the isotopic composition of the ice shifts with the climate that produced it. Reading the ratio of heavy to light oxygen across the depth of a core produces a continuous temperature record stretching back across the entire length of the archive. Dust is another layer of information. During cold, dry glacial periods, winds were stronger and the land was more exposed. Dust from deserts and dry steppes was carried far into the polar regions and fell with the snow. Glacial ice layers are visibly dustier than interglacial ones, and the mineral content of that dust points to where it originated. Some dust found in Antarctic cores was blown from Patagonia. Some came from Australian deserts, carried halfway around the planet. Pollen grains also travel on the wind and settle into the ice. A pollen layer in a core tells researchers what plants were growing in nearby regions when that layer was deposited. The presence of certain tree pollens signals a warm period. Grasses and tundra plants indicate cold. Over deep time, this record shows entire ecosystems shifting across continents, forests advancing and retreating across hundreds of kilometers as temperatures rose and fell over thousands of years. Volcanic eruptions leave their signature too. Ash and sulfate particles from major eruptions are distributed globally before settling onto the ice. These layers appear as sharp chemical spikes in the core and can be matched to known historical eruptions with considerable precision. The 1815 eruption of Mount Tambora, which caused the year without a summer, is visible in cores from both poles. Eruptions from thousands of years before written records appear with the same clarity. As glaciers shrink, they release objects locked inside them for centuries or millennia. Ancient forests emerge from beneath retreating ice in Alaska and Scandinavia. Trees still rooted in their original soil, preserved by cold and low oxygen for thousands of years. Animal remains appear with fur and soft tissue intact. In some cases, the material is well enough preserved to yield ancient DNA, offering direct access to species and populations that no longer exist anywhere on Earth. Human artifacts emerge as well. Glaciers crossing high alpine passes have released Roman-era coins, leather sandals, wooden tools, and textile fragments. In the Canadian Arctic, retreating ice patches have exposed hunting tools made from organic materials that would not survive in any other environment, throwing sticks, arrow shafts, and cordage dating back thousands of years. The ice did not destroy these objects. It held them exactly as they were left. The most famous glacial discovery was made on a September afternoon in 1991, when two hikers crossing the Itztal Alps noticed something protruding from melting ice. What they found was a man lying face down in a rocky hollow, his equipment scattered around him, his body preserved in extraordinary detail by the cold and dry conditions of the glacier that had covered him for more than 5,000 years. He is known as Tsi, named for the valley where he was found. Analysis of his body revealed a life in remarkable detail. He carried a copper axe, a bow with arrows, a fire-starting kit, and food. His last meal, consumed hours before his death, included red deer, ibex, einkorn wheat, and various plants. His clothing was assembled from multiple animal species with considerable skill. He was approximately 45 years old, well-traveled, and in reasonable health for his time. Tsi did not die peacefully. An arrowhead was found embedded in his left shoulder, severing a major artery. The wound would have been fatal within minutes. He was murdered, probably in an ambush, and came to rest in the hollow where ice sealed over him and held him for 53 centuries. The glacier that preserved him is retreating. Researchers estimate that had those hikers arrived a few decades later, C might have been lost to meltwater before anyone found him. Antarctica holds approximately 90% of all the fresh water on Earth, almost entirely in the form of ice. The ice sheet covering it reaches nearly 5 kilometers in thickness in places, pressing down on the bedrock with a weight that has depressed the continent by hundreds of meters. If the ice were removed, Antarctica would slowly rise, as parts of Scandinavia are still rising today after losing their own ice sheets at the end of the last glacial period. The continent beneath the ice is not flat. Antarctica has mountain ranges, valleys, and plains buried under kilometers of frozen water. The transantarctic mountains divide it into 2 distinct ice sheets. The East Antarctic ice sheet is larger, older, and more stable. The West Antarctic ice sheet sits partly below sea level and is considered far more vulnerable to warming. In places, the bedrock beneath it lies more than 2 kilometers below the ocean surface. Greenland holds the second largest ice sheet on Earth, covering roughly 80% of the island. If fully melted, it contains enough water to raise global sea levels by approximately 7 meters. Greenland loses ice through surface melting in summer and through glaciers that flow to the coast and calve into the sea. The Jakobshavn Glacier, one of the fastest moving on Earth, advances toward the coast at rates exceeding 40 meters per day in active seasons. The sea ice covering the Arctic Ocean is a different kind of ice entirely. It is frozen seawater floating on the ocean's surface, not land ice, not stored fresh water. Because it is already in the ocean, its melting does not directly raise sea levels. What it does instead is regulate temperature, reflect sunlight, and support an entire ecosystem built around its seasonal rhythms. Its decline reshapes the Arctic in ways that extend well beyond the region itself. The distinction between sea ice and land ice matters enormously for sea level calculations. Arctic sea ice, already floating, contributes almost nothing to sea level rise when it melts. The threat comes from land-based ice, from Greenland, from the Antarctic ice sheets, and from the thousands of mountain glaciers distributed across every continent. When that ice melts, water previously stored on land enters the ocean for the first time. There are approximately 200,000 glaciers worldwide outside the polar regions, and the majority are losing mass. Their combined contribution to sea level rise is significant, comparable in the near term to contributions from the large ice sheets. These are the glaciers most people will never see, but whose retreat is felt directly in the water supplies of hundreds of millions of people living downstream from mountain ranges on every inhabited continent. In many mountain regions, glaciers function as slow-release reservoirs. They store winter precipitation as ice and release it gradually through summer meltwater, keeping rivers flowing through the dry season after seasonal snowmelt is stopped. As glaciers shrink, this buffer disappears. Rivers that once ran year-round begin running low or dry in late summer, affecting agriculture, drinking water, and hydroelectric generation across regions that have depended on glacial meltwater for centuries. Permafrost is ground that remains frozen for at least 2 consecutive years. It underlies roughly a quarter of the northern hemisphere's land surface, large parts of Siberia, Canada, and Alaska, and in some places reaches depths of over a kilometer. The layer above it thaws each summer and refreezes each winter, but the permafrost beneath has held steady through centuries of relatively stable climate. That stability is now changing in measurable ways across the Arctic. What permafrost contains is the reason it matters beyond the land itself. Over thousands of years, organic material accumulated in the frozen ground and was preserved rather than decomposed, because the microorganisms that break down organic matter cannot function in frozen conditions. Estimates suggest permafrost stores roughly twice as much carbon as is currently in the atmosphere. As it thaws, that material becomes available to microbial activity and is released as carbon dioxide and methane. Methane is a greenhouse gas roughly 80 times more potent than carbon dioxide over a 20-year period. Releases from thawing permafrost add to the warming that is causing the thaw, which releases more methane, which accelerates warming further. In parts of Siberia, bubbles of methane rising through thawing lakes have been documented in quantities large enough to be ignited at the surface. This feedback loop is one of the more closely monitored elements of contemporary climate science. The ground itself changes as permafrost thaws. Roads buckle and sink as the frozen substrate beneath them softens. Buildings tilt. Coastlines erode far faster than in non-permafrost regions because the frozen ground that once resisted wave action becomes soft enough to be cut away rapidly by the sea. In some Arctic communities, the ground that generations of people have built their lives on is becoming structurally unreliable in ways that have no precedent in living memory. Arctic sea ice has been declining for decades. The extent of summer sea ice has shrunk by roughly half since satellite observations began in 1979, and its thickness has dropped as well. Ice that once survived multiple winters, growing thicker and more consolidated year by year, is being replaced by younger, thinner ice that melts more readily each summer. The Arctic that existed 50 years ago and the one that exists now are measurably, visibly different places. The ice that remains in the Arctic today is younger on average than it was 2 decades ago. First-year ice, formed in a single winter, now dominates where multi-year ice once prevailed. It is thinner, saltier, and structurally weaker. Ships that once required icebreakers to navigate certain Arctic routes now pass through open water in late summer. The Northwest Passage, which explorers spent centuries attempting to cross, has become navigable without specialized vessels. The consequences of that shift move outward from the Arctic in ways that climate scientists are still mapping. A warmer Arctic reduces the temperature difference between the poles and the mid-latitudes, which appears to affect the jet stream, the high-altitude wind current that steers weather systems across the northern hemisphere. A more sluggish, meandering jet stream allows weather patterns to stall, contributing to extended heat waves and flooding events. These connections between Arctic ice loss and mid-latitude weather are still being studied and debated, but the direction of the evidence is consistent. What happens at the top of the world does not stay there. The Arctic has always been the planet's thermostat, and as its ice diminishes, the system it regulates becomes less predictable. The change is not coming. For the communities and ecosystems already living with it, the change is the present condition. The mountain glaciers of the Himalayas feed some of the largest river systems on Earth. The Ganges, the Indus, the Brahmaputra, the Yangtze, all draw from glacial meltwater originating in the high ranges of Central Asia. Roughly 2 billion people live in watersheds that depend on these rivers. For many of them, the connection to glacial ice is not abstract. It is the water that arrives in summer, fills irrigation canals, and keeps cities supplied through the dry months between monsoons. The Alps have lost more than half of their glacial volume since the mid-19th century. The glaciers that define the landscape of Switzerland and Austria are visibly smaller than they were even 30 years ago. Some have disappeared entirely. Scientists project that under current warming trajectories, the Alps could lose 80 to 90% of remaining glacial ice by the end of this century. What was white and moving for thousands of years is becoming bare rock. The Andes hold the largest concentration of tropical glaciers in the world. At high altitudes near the equator, glaciers have long supplied water to cities including La Paz and Quito. The Quilcaya ice cap in Peru, the largest tropical ice cap on Earth, has been retreating at an accelerating rate since the 1970s. Ice, that took centuries to accumulate, is being lost within decades, and what replaces it is not another water source, but exposed rock and thin air. As glaciers retreat, they sometimes leave behind lakes held in place by a dam of glacial debris called a moraine. These glacial lakes can be unstable. The moraine dam is made of loose sediment and ice, and if it fails, through an earthquake, a landslide, or the gradual melting of ice within the dam itself, the lake can empty catastrophically. This is known as a glacial lake outburst flood, or GLOF, and the volumes of water released can be enormous. GLOF events have destroyed villages, bridges, roads, and farmland across the Himalayas, the Andes, and Central Asia. In 1941, a glacial lake outburst in Peru killed an estimated 6,000 people when it sent water and debris through the city of Haraz. A 2021 event in the Indian state of Uttarakhand swept away 2 hydroelectric dams and killed over 200 people. The number of glacial lakes is growing as glaciers retreat, and so is the number of people living downstream. When sea ice covers the ocean, it reflects a significant portion of incoming solar radiation back into space. This reflective property is called albedo, and sea ice has one of the highest albedo values of any natural surface, reflecting up to 80% of incoming sunlight. Open ocean, by contrast, absorbs roughly 90% of solar energy. When sea ice melts and ocean water is exposed, the surface shifts from highly reflective to highly absorptive. This transition creates a feedback loop. As ice melts and dark ocean water is exposed, the surface absorbs more heat, which warms the water, which melts more ice, which exposes more dark water. The Arctic is warming at roughly 4 times the global average rate, and the ice albedo feedback is a primary reason. The loss of sea ice is not only a symptom of warming, it is also an amplifier, and the two processes reinforce each other continuously. Beneath the Antarctic ice sheet, hidden under kilometers of frozen water and cut off from the surface for millions of years, there are lakes. More than 400 subglacial lakes have been identified beneath Antarctica. The largest is Lake Vostok, discovered beneath a Russian research station in the 1990s, approximately 250 kilometers long, 50 kilometers wide, and sitting under roughly 4 kilometers of ice. Lake Vostok has been isolated from the surface for an estimated 15 to 25 million years. The water in it is ancient beyond easy comprehension, sealed away before humans existed, before the ice sheet above it fully formed. Russian scientists finally penetrated to the lake in 2012 after decades of drilling. The conditions inside are extreme. Complete darkness, enormous pressure, near freezing temperatures, and no exchange with the surface world for geological timescales. What lives in Lake Vostok has been the subject of intense scientific interest. Samples recovered from the ice just above the lake have contained DNA traces, suggesting the presence of microbial life. The organisms, if confirmed, would represent life adapted to conditions unlike almost anything on the surface of Earth. Isolated, pressurized, lightless, and ancient. Whether they are active or dormant, whether they represent a single ecosystem or many, remains an open question. Subglacial environments across Antarctica and the Arctic have shown that ice is not the sterile barrier it appears. Microbial communities have been found in ice cores, in the thin water films between ice crystals, and in the sediment beneath glaciers. Some metabolize on traces of chemical energy locked in surrounding rock. Others enter dormancy, lasting thousands of years before conditions allow activity again. Life in ice does not thrive, but it persists. Bacteria recovered from Siberian permafrost have been revived after hundreds of thousands of years frozen. Ancient viruses, some over 30,000 years old, have been extracted from permafrost and shown capable of infecting host cells under laboratory conditions. In 2021, researchers identified 42 novel virus groups in a Tibetan glacier ice core dating back 15,000 years. None were known to science before that core was analyzed. The microorganisms preserved in ice represent an archive of life from periods that left almost no other biological record. Studying them offers a window into how life adapted to past climates and how microbial communities responded to environmental change. They also raise questions about what might persist in the icy subsurface oceans of Europa or Enceladus. The ice preserves what nothing else could, and what it holds is still, in large part, unread. Life does not stop at the freezing point. In the coldest, darkest environments on Earth, beneath sea ice, inside glaciers, within frozen Arctic ground, organisms have found ways not merely to survive, but to function. Some have been doing so for hundreds of millions of years, long before the first warm-blooded animal appeared. The strategies they use are varied, precise, and in several cases have no equivalent anywhere else in the natural world. Under the sea ice of the Arctic and Antarctic, the underside of the ice is not a smooth surface, but a complex landscape of channels and cavities colonized by dense communities of ice algae. These organisms photosynthesize using the dim light that filters through the ice above, forming the base of a food web that supports krill, fish, seals, and the large predators above them. Remove the ice, and the entire foundation of that web disappears. The ice algae communities beneath polar sea ice are not only food sources. They also produce dimethylsulfonaceae, a compound that bacteria break down into dimethyl sulfide, a gas that rises into the atmosphere and influences cloud formation. Sea ice algae, in other words, play a small but real role in regulating the climate of the regions above them. The biology of the ice and the physics of the atmosphere are connected in ways that took decades to untangle. The fish living beneath polar ice face a problem that would kill most vertebrates. Seawater at the poles can drop to minus 1.8 degrees Celsius, below the normal freezing point of fish blood. Antarctic icefish and Arctic cod have independently evolved a solution: antifreeze proteins that bind to ice crystals as they begin to form and prevent them from growing. The proteins do not lower the freezing point chemically. They block ice growth at the molecular level. These antifreeze proteins were first identified in Antarctic nodothenoid fish in the 1960s by biologist Arthur de Vries. What he found were glycoproteins, sugar protein compounds that coated ice crystal surfaces and interrupted their growth. Similar proteins have since been found in Arctic fish, insects, plants, fungi, and bacteria evolved independently across the tree of life, in organisms with no common ancestor, all facing the same problem. The wood frog of North America takes a different approach entirely. Rather than preventing ice from forming, it allows it. When winter arrives, the wood frog freezes. Ice forms between its cells, its heart stops beating, its breathing ceases. Up to 65% of the water in its body becomes ice. It remains this way for weeks or months, then thaws in spring and resumes normal activity within hours. The wood frog survives through mechanisms that work together with precision. As freezing begins, the frog rapidly converts liver glycogen into glucose, flooding its cells with sugar. This concentration of glucose acts as a cryoprotectant, reducing how much water freezes inside the cells and cushioning them against the damage that ice crystals would otherwise cause. The cells are not unharmed, but they are protected well enough to resume function when warmth returns. Tardigrades, microscopic animals less than a millimeter long, found in moss, soil, and water on every continent, carry cold tolerance to an extreme no other multicellular animal approaches. When conditions become hostile, a tardigrade enters cryptobiosis, expelling nearly all the water from its body and curling into a dried pellet called a tun. Its metabolism drops to less than 1% of normal activity. It is not dead, but barely alive in any measurable sense. In cryptobiosis, tardigrades can survive temperatures close to absolute zero, boiling water, high-dose radiation, the vacuum of space, and pressures greater than the deepest ocean trench. They have been revived after decades in this state. The mechanism involves specialized proteins unique to tardigrades that form a glass-like substance around cellular components during desiccation, physically shielding them from damage, a solution with no known equivalent in any larger animal. Many insects survive winter cold by managing it chemically. The goldenrod gallfly larvae of North America and various Arctic beetle species produce polyols, compounds including glycerol and sorbitol that accumulate in body fluids as temperatures drop. These lower the freezing point of the insect's internal fluids, and in some species allow supercooling to temperatures as low as -50 degrees Celsius without any ice formation at all. Other insects take the freeze-tolerance approach of the wood frog, deliberately allowing ice to form in extracellular spaces while protecting cells from intracellular freezing. The timing is controlled through ice-nucleating proteins that trigger crystallization at a specific temperature, cold enough to begin the process in a controlled way, but not so suddenly that cells are damaged. The difference between a lethal freeze and a survivable one can come down to the rate at which ice forms. Some of the most extreme cold-adapted organisms are not animals or plants, but bacteria. Psychrophiles, cold-loving microbes, thrive at temperatures where most life cannot function. They have been found in Antarctic ice cores, in brine channels running through sea ice, and in the sub-zero waters beneath ice shelves. Their enzymes remain flexible at low temperatures, where conventional proteins become rigid and stop working. They are built for cold, the way other organisms are built for warmth. The variety of cold survival strategies across the living world reflects the fact that ice has been a recurring challenge throughout the history of life. Every ice age, every winter, every cold snap has been a selective pressure. Some organisms prevented freezing, some controlled it, some endured it in suspended existence until conditions improved. Each strategy is a different answer to the same question. What do you do when the water around you turns to ice? What is striking is how many of these solutions were discovered independently by organisms with no evolutionary connection. Antifreeze proteins evolved separately in Antarctic and Arctic fish, in insects, and in plants. Freeze tolerance appeared in frogs and insects through entirely different biochemical pathways. Cryptobiosis exists in tardigrades, nematodes, plants, and bacteria. The same problem solved repeatedly by different lineages across hundreds of millions of years. Researchers study these mechanisms not only out of biological curiosity, but for practical reasons. Antifreeze proteins have applications in food preservation and in protecting transplant organs during cold storage. The compounds that protect wood frog cells during freezing have informed research into surgical cooling of human tissue. What evolution developed for winter survival may yet find uses in medicine that its inventors could not have anticipated. The human body responds to cold in ways that are immediate, layered, and in some cases, surprisingly adaptive. When skin temperature drops, blood vessels near the surface constrict, redirecting flow away from the extremities and toward the core. The hands and feet become cold first. This is not a malfunction. It is the body protecting its most critical organs by concentrating warmth where it matters most. Shivering follows. Muscles contract involuntarily in rapid cycles, generating heat through movement. It is metabolically expensive, but effective in still air. The problem is that water conducts heat away from the body roughly 25 times faster than air does. In cold water, shivering alone cannot keep pace with the loss, and the body's ability to maintain core temperature begins to fail within minutes, depending on water temperature and body composition. Hypothermia begins when core body temperature drops below 35 degrees Celsius. Shivering may stop, not because the body has warmed, but because muscles no longer have the energy to sustain it. Judgment becomes impaired. Coordination fails. The sensation of cold may paradoxically diminish, which is why people in severe hypothermia sometimes remove their clothing, a behavior known as paradoxical undressing, observed consistently enough to have a clinical name. Below 30 degrees Celsius, the heart becomes vulnerable to arrhythmia, irregular electrical rhythms that can stop it entirely. Below 28, the risk of cardiac arrest rises sharply. Yet hypothermia is also one of the few conditions in which a person can survive cardiac arrest and be resuscitated. The cold that stopped the heart also slowed every metabolic process in the body, reducing the brain's oxygen demand to a fraction of its normal requirement. There are documented cases of people surviving without heartbeat for over an hour in cold water. In 1999, a Swedish doctor named Anna Bagenholm fell through ice while skiing and spent 80 minutes submerged in near-freezing water. Her heart had stopped for over an hour when rescuers reached her. She was revived after rewarming in hospital and recovered almost completely. Her case changed how emergency medicine thinks about the relationship between cold and cardiac arrest. This protective effect has been deliberately applied in medicine. Therapeutic hypothermia involves cooling a patient to between 32 and 36 degrees Celsius after cardiac arrest or brain injury. At lower temperatures, the brain's demand for oxygen drops, and the cellular damage that follows oxygen deprivation slows significantly. Controlled cooling is now standard after cardiac arrest in hospitals across many countries, and the evidence for its benefit is substantial. Cooling is also used during surgery. In procedures involving the heart or major blood vessels, surgeons sometimes cool the body to temperatures as low as 18 degrees Celsius, a state called deep hypothermic circulatory arrest. At that temperature, the brain can tolerate the absence of blood flow for periods that would cause irreversible damage at normal body temperature. The patient is functionally suspended, not dead, not conscious, while the surgeon works. The idea of extending this principle indefinitely is the premise of cryonics. Organizations such as Alcor in the United States offer to preserve legally deceased bodies or brains in liquid nitrogen at -196 degrees Celsius, in the hope that future technology will allow revival and repair. Several hundred people have been preserved this way since the practice began in the 1960s. The legal, ethical, and scientific questions surrounding cryonics remain deeply unresolved. The central problem is ice. When human tissue freezes without preparation, ice crystals form inside and between cells, rupturing membranes and destroying fine structure. Cryonics organizations address this using cryoprotectant solutions that replace water in tissues with chemicals that vitrify, solidifying into a glass-like state without forming damaging crystals. Whether this preserves enough structural and neural detail to allow future revival is a question current science cannot answer. The brain's complexity, roughly 86 billion neurons forming trillions of synaptic connections, means even minor structural damage could be irreversible in ways no future technology could correct. Critics argue that legal death already involves enough cellular damage to make revival impossible. Proponents argue the alternative, burial or cremation, guarantees permanent loss. The debate is not resolvable with current science, which is precisely what makes it persist. Organ transplantation depends on cold in a more practical and immediate way. When an organ is removed from a donor, cold slows metabolism, reducing the rate at which cells consume oxygen and accumulate damage. Most organs are packed in ice or cooled preservation solutions immediately after removal. A heart can typically be preserved for 4 to 6 hours. A kidney can last up to 36 hours. These windows define the entire logistics of transplantation. Machine perfusion, in which organs are flushed with cold oxygenated solution rather than stored on ice, has extended viability windows and improved outcomes for difficult cases. Livers that would have been discarded under static cold storage have been successfully transplanted after machine perfusion. The careful management of temperature and cellular chemistry that allows a wood frog to survive freezing is being applied, with increasing sophistication, to human organs outside the body. Cold water immersion triggers one of the most dramatic reflexes in the human body. When the face is submerged in cold water, heart rate drops almost immediately, sometimes by 50% within seconds. Blood is redirected toward the heart, lungs, and brain. Breathing slows. This is the mammalian dive reflex, shared by humans, seals, and dolphins, functioning as an automatic physiological preparation for submersion that evolution preserved across millions of years. In young children and in cases of sudden cold immersion, the dive reflex can preserve brain function for remarkably long periods without oxygen. Children have been recovered from cold water after submersion times of 30 minutes or more and survived with little neurological damage. The cold suppressed metabolism fast enough to protect the brain before hypoxia could cause irreversible injury. In medicine, this is sometimes expressed simply: you are not dead until you are warm and dead. The relationship between cold and the human body is not only one of threat and response. Cold has been used deliberately for thousands of years to preserve food, treat injury, and reduce fever. Contemporary cryotherapy exposes the body to extreme cold for recovery benefits. The mechanisms explored in modern medicine and the instinct that drove ancient people to pack wounds in snow share the same recognition. Cold slows things down, and sometimes that is exactly what is needed. Ice is not a feature unique to Earth. It is one of the most abundant solid materials in the solar system, present on every planet cold enough to sustain it, on dozens of moons, in the rings of the outer planets, and throughout the asteroid belt. The solar system is, in a fundamental sense, built largely around frozen water. Earth, with its liquid oceans and thin seasonal ice, is the exception. The frozen worlds are the rule. The distribution of ice follows temperature and distance from the sun. In the inner solar system, temperatures are too high for water ice to persist on exposed surfaces. But beyond a boundary called the frost line, located roughly between the orbits of Mars and Jupiter, water ice becomes stable. Beyond that line, ice is everywhere. It fills the cores of comets, coats the surfaces of distant moons, and forms the rings of Saturn. The evidence for Europa's subsurface ocean comes from multiple sources. The Galileo spacecraft detected a magnetic field that fluctuates in a way consistent with the conducting layer beneath the surface. Salt. Water is an electrical conductor in a way that solid ice is not. The surface also shows features consistent with ice floating on liquid: fractures, pressure ridges, and regions where the surface appears to have broken apart and refrozen in new configurations. Europa's ocean is kept liquid not by solar heat, but by tidal forces. Jupiter's immense gravity flexes the moon as it orbits, generating friction and heat in its interior. This tidal heating maintains liquid water at depth, despite Europa's enormous distance from the sun. The same mechanism drives the volcanic activity on Io, Europa's neighbor, the most volcanically active body in the solar system, demonstrating how powerful gravitational flexing can be as an energy source. NASA's Europa Clipper spacecraft launched in October 2024 and is en route to the Jovian system. It will conduct dozens of close flybys beginning around 2030, analyzing surface composition, measuring the thickness of the ice shell, and searching for signs of the ocean below. If the ocean exists as the evidence suggests, Europa becomes one of the most compelling candidates in the solar system for the existence of life beyond Earth. Saturn's moon Enceladus offers something Europa can only suggest: direct access to subsurface water. Enceladus is small, barely 500 kilometers across, but near its south pole, a series of fractures nicknamed tiger stripes erupt continuously, sending plumes of water vapor, ice particles, and organic compounds hundreds of kilometers into space. Enceladus is venting its interior directly to the universe, making it one of the most extraordinary objects in the solar system. The Cassini spacecraft flew through these plumes between 2005 and 2017 and analyzed their composition. The plumes contain water, carbon dioxide, methane, and molecular hydrogen. The presence of molecular hydrogen indicates ongoing reactions between water and hot rock in the interior. Hydrothermal activity. On Earth, hydrothermal vents on the ocean floor support ecosystems entirely independent of sunlight. Enceladus appears to have the same conditions operating beneath its ice. Mars presents a different picture. The planet is cold and dry at the surface, but carries ice in several forms. Both poles are capped with water ice and carbon dioxide ice. The North Polar Cap is predominantly water ice beneath a seasonal layer of frozen carbon dioxide. Together, the Martian polar caps hold enough water that if fully melted, it would cover the entire planet in a shallow global ocean. Beneath the Martian surface, the situation may be more complex. In 2018, the Marsis radar instrument aboard Mars Express detected a strong reflection beneath the South Polar Cap, interpreted as a subglacial lake approximately 20 kilometers wide. Subsequent analysis suggested additional buried lakes in the same region. The water, if liquid, is likely extremely salty. Salt lowers the freezing point enough for liquid water to persist at the temperatures found at that depth. Mars also carries ice buried under thin soil across its mid-latitudes. Observations from orbit and surface missions have revealed extensive subsurface ice deposits at depths of less than a meter across large areas of the planet. This ice is a legacy of past climates when Mars's axial tilt was different and ice accumulated at lower latitudes. It represents both a potential water resource for future human missions and a possible habitat for microbial life. The ice on Mars tells a story of a planet that was once wetter and warmer. Ancient riverbeds, lake basins, and delta formations visible from orbit indicate that liquid water flowed on the surface billions of years ago. What caused Mars to lose most of its water, whether it escaped into space, froze into the subsurface, or both, is one of the central questions of planetary science. The ice that remains is a remnant of that earlier world. Mercury, the closest planet to the Sun, also carries ice. Permanently shadowed craters near its poles never receive sunlight, and temperatures there drop to minus 180 degrees Celsius or lower. Radar observations first suggested ice in the 1990s, and the Messenger spacecraft confirmed it in 2012. The ice is thought to have been delivered by comets and asteroids over billions of years, preserved in cold traps where it has remained ever since. Ganymede, the largest moon in the solar system, is also believed to harbor a subsurface ocean. It is the only moon known to generate its own magnetic field, and measurements suggest a saltwater layer deep within its interior. Callisto, the outermost of Jupiter's large moons, may have a similar structure. The possibility that multiple ocean worlds exist within a single planetary system has changed how scientists think about the distribution of habitable environments across the solar system. The number of icy worlds in the outer solar system has shifted the framework of astrobiology. For decades, the search for life beyond Earth focused on the habitable zone, the narrow band where liquid water can exist on a planet's surface. The discovery that tidal heating can maintain liquid oceans far outside that zone, beneath thick ice shells, has expanded the concept of habitability to include a far larger portion of any solar system than previously imagined. Comets are among the oldest objects in the solar system, formed in the cold outer reaches where the sun's heat never reached during planetary formation. They are frozen time capsules, dense cores of ice, dust, and organic compounds that have changed little in 4.5 billion years. When a comet's orbit carries it close to the sun, the ice on its surface sublimates, releasing gas and dust that form the luminous tail. That tail is ancient water and carbon, briefly made visible. The ice in comets is not pure water. It is a mixture of water ice, carbon dioxide, carbon monoxide, methane, and ammonia, along with complex organic molecules. When the Rosetta spacecraft orbited Comet 67P Churyumov-Gerasimenko between 2014 and 2016. Its instruments detected more than 400 distinct organic compounds in the comet's outgassing, including glycine, the simplest amino acid, and phosphorus, an essential element for DNA and cell membranes. Comets have been delivering this material to planets throughout the history of the solar system. During the late heavy bombardment, roughly 4 billion years ago, the inner solar system was subjected to an intense barrage of comets and asteroids. The water in Earth's oceans may partly originate from this period, delivered as ice in comets that vaporized on impact. The precise proportion is still debated, but the contribution of cometary ice to Earth's water budget is considered significant. The role of ice in the origin of life extends beyond delivering water. Ice surfaces in the cold reaches of space act as chemical reaction sites. When ultraviolet radiation from stars strikes ice-coated dust grains in interstellar clouds, it drives reactions that would not occur in the gas phase alone. Laboratory experiments replicating these conditions have produced amino acids and nucleobases, the building blocks of RNA and DNA, starting from nothing more than simple ices. Water ice is one of the most common molecules in the universe. It has been detected in interstellar clouds, in the disks surrounding young stars, on asteroids, and in the envelopes of dying stars. In dense molecular clouds where stars form, water ice coats tiny dust grains layer by layer over millions of years. When those clouds collapse to form new solar systems, that ice becomes part of the raw material from which planets and comets are assembled. The James Webb Space Telescope has brought ice detection to a new level of precision. In 2023, Webb confirmed crystalline water ice in a debris disk around a young star called HD 181327, about 160 light-years from Earth. The detection revealed ice mixed with fine dust in a cold region of the disk, direct evidence of the same kind of icy reservoir that likely existed in the early solar system before planets fully formed. Webb has also begun characterizing the atmospheres of exoplanets with sensitivity that previous telescopes could not achieve. Early observations have detected water vapor, carbon dioxide, and other molecules in exoplanet atmospheres. Some planets observed are in temperature ranges where water could exist as ice on their surfaces or in their upper atmospheres. The telescope is providing, for the first time, a direct chemical window into worlds around other stars. The presence of ice on a planet does not by itself indicate habitability. What matters is whether that ice connects to liquid water, chemical energy, and organic molecules. Europa and Enceladus are compelling not simply because they have ice, but because their ice sits above or around liquid, water in contact with rock and heat. That combination, water, chemistry, energy, is what life on Earth requires, and it appears to exist in frozen worlds far from the sun. Ice also plays a structural role in planet formation. In the early solar system, ice grains in the disk around the young sun were building blocks from which the outer planets grew. Jupiter, Saturn, Uranus, and Neptune all contain large quantities of water, ammonia, and methane ice. Uranus and Neptune are sometimes called ice giants for this reason. Their bulk composition is dominated by ices rather than the hydrogen and helium that make up most of the two larger planets. The rings of Saturn are composed almost entirely of water ice, particles ranging from tiny grains to chunks several meters across. They are extraordinarily reflective, visible even through a modest telescope. Current estimates suggest the rings formed between 10 and 100 million years ago, long after the dinosaurs appeared on Earth. Saturn's rings are not an ancient feature of the solar system. They are recent, and they will not last forever. Ice connects every part of the solar system to every other. The water in a glass on Earth shares its atomic history with ice in a comet beyond Neptune, with frost on a Martian crater wall, with the ocean beneath Europa's crust. The hydrogen and oxygen atoms in that water were forged in stars that died before the sun was born. Ice is not simply frozen water. It is the most common form of one of the universe's most consequential molecules, and it is everywhere. For most of human history, ice was a seasonal accident, something that arrived in winter, melted in spring, and could not be stored, traded, or relied upon. That changed in the early 19th century when a young Boston merchant named Frederick Tudor decided to treat ice as a commodity. In 1806, Tudor loaded a ship with ice cut from a Massachusetts pond and sailed it to Martinique in the Caribbean. The ice mostly melted before it could be sold. Tudor lost money. He tried again. Tudor's persistence eventually changed not only his fortune, but the way the world ate and stored food. He developed better insulation techniques, packing ice in sawdust, building purpose-designed ice houses, and established a global distribution network. By the 1850s, his operation was shipping ice from New England to India, Australia, and South America. Ice harvested from a Massachusetts pond was cooling drinks in Calcutta. The cold had become a product. The ice trade created entire industries. Harvesting from frozen ponds became a major winter occupation across the northeastern United States. Thousands of workers used ice saws and horse-drawn scrapers to extract enormous quantities each winter, stored in insulated warehouses until summer. At its peak, the natural ice industry employed tens of thousands of people and supplied homes, hospitals, and businesses across the developed world. The scale of the natural ice industry at its height was remarkable. In a single year during the 1880s, the United States harvested and shipped an estimated 25 million tons of natural ice. The Wenham Lake Ice Company in Massachusetts supplied ice to Queen Victoria's household in England. Boston ice was considered the finest in the world, its clarity and purity a matter of civic pride. Ice had become a luxury export, and the American Northeast was its capital. The industry collapsed within a generation. Mechanical refrigeration, developed in the latter half of the 19th century, made natural ice commercially obsolete. By the early 20th century, the trade had largely disappeared, but the infrastructure Tudor built, the ice houses, the delivery networks, the expectation of cold storage, shaped how refrigeration technology was adopted when it arrived. His industry made refrigeration feel necessary before refrigerators existed. While the ice trade was industrializing cold and temperate climates, Arctic peoples had been building with ice for thousands of years. The igloo, from the Inuit word igloo, meaning house, is a precise engineering achievement. A well-built igloo maintains an interior temperature around 16 degrees Celsius when outside temperatures reach -40. Ice is an excellent insulator, and the dome shape distributes weight evenly without internal supports. Construction follows a careful method. Blocks of compact snow are cut in a spiral from the building site floor and stacked in a rising, inward curving wall. The final top block locks the spiral into a self-supporting dome. A small ventilation hole at the apex prevents carbon dioxide buildup. Body heat and cooking do the rest. In communities where timber was unavailable, the igloo was one of the most thermally efficient shelters ever built. The modern ice hotel takes a different relationship with the material, one of spectacle rather than survival. The original ice hotel in Jukkasjärvi, Sweden, was created in 1989 near the Torn River. Every winter since, it has been rebuilt from scratch using ice harvested from the river. Walls, furniture, beds, chandeliers, and sculptures, all made entirely of ice. Artists from around the world are invited each year to design individual suites. The ice hotel melts each spring and is rebuilt each winter, making it one of the few hotels designed to disappear. It maintains a temperature around -5 degrees Celsius inside, cold enough to keep the structure stable, warm enough to sleep in with the right gear. A permanent heated section was added in 2016, kept frozen year-round by refrigeration. The impermanence of the original structure is, for many visitors, exactly the point. China takes ice architecture further than anywhere else. Every winter in Harbin, in the northeastern Heilongjiang province, an entire city rises from the Songgur River. The Harbin Ice and Snow Festival, held annually since 1963, produces structures on a scale that surprises first-time visitors. Full-scale replicas of famous buildings illuminated from within by colored lights, some reaching 30 meters in height. At its peak, the festival draws millions of visitors. Like all ice architecture, it disappears completely by spring. Ice has also shaped one of the most universal foods in human history. The practice of flavoring and cooling food with ice or snow appears independently across multiple ancient cultures. In China, frozen mixtures of rice and snow were consumed as far back as the Tang dynasty, around the 7th century CE. Arab traders in the medieval period mixed fruit syrups with mountain snow to produce sharbet, the drink that eventually became sorbet and sherbet in Europe. Roman emperors sent runners into the mountains to collect snow, which was then flavored with fruit, honey, and wine for banquets. The Emperor Nero is said to have been particularly fond of it. These early frozen treats bore little resemblance to modern ice cream, which requires the controlled freezing of a cream-based mixture, a technique not developed until dairy farming and sugar production became sufficiently advanced in early modern Europe. The development of ice cream depended on understanding freezing physics. Mixing salt with ice lowers the temperature of the mixture significantly below zero, creating conditions cold enough to freeze cream packed inside it. This technique, adopted widely in 17th century Europe, made it possible to produce frozen cream in commercial quantities. Ice cream vendors were common on the streets of London and Paris by the 18th century. The cultural weight of ice in food goes beyond ice cream. Iced drinks, cold storage of perishables, chilled seafood markets, all of these depend on a supply of reliable cold that for most of human history simply did not exist outside of winter. The ability to keep food cold year-round transformed diet, extended the range over which perishable food could be traded, and reduced foodborne illness. The history of refrigeration is, in part, a history of how ice made the modern food supply possible. The first ice cream parlor in the United States opened in New York City in 1776. By the mid-19th century, ice cream had become available to ordinary people, partly because of the ice trade Tudor had built. The ice cream cone was reportedly introduced at the 1904 World's Fair in St. Louis, when a waffle vendor improvised a cone for a neighboring vendor who had run out of dishes. Whether the story is entirely accurate, the cone spread rapidly and has never gone away. Ice entered Western painting seriously in the 17th century, when Dutch and Flemish artists began depicting frozen canals with a precision that went beyond seasonal scenery. Hendrik Averkamp, who was deaf and spent his life observing the world in silence, produced some of the most detailed ice paintings in the tradition. Crowded scenes of skaters and vendors on frozen Dutch waterways, recorded with the patience of someone who had learned to watch instead of speak. By the 19th century, ice had become something more than backdrop. J.M.W. Turner painted several scenes involving frozen seas, most notably a work depicting the Franklin expedition to the Arctic. Dense and atmospheric, it arrived before news of the expedition's fate had reached England. When the disappearance was confirmed years later, Turner's image took on a different weight. He had painted the danger before the public knew the danger was real. Ice sculpture as a formal tradition has older roots than most people assume. Records of decorative ice structures appear in 17th century Russia, where elaborate palaces were built for winter celebrations. By the 18th century, the practice had spread across European courts. Today, competitions are held worldwide, from culinary events with precisely carved centerpieces to outdoor festivals where artists work with chainsaws on blocks, weighing hundreds of kilograms. Ice takes on its most powerful literary form at the extremes. In stories set in the Arctic or Antarctic, where it becomes something more than weather. Mary Shelley's Frankenstein begins and ends in the Arctic. The novel opens with an explorer pushing toward the North Pole through frozen seas and closes with the monster disappearing into the ice. The frozen landscape is not merely setting. It is a mirror for isolation, ambition, and the limits of human reach. H.P. Lovecraft extended this tradition in 1936 with At the Mountains of Madness, set in the Antarctic interior. His explorers discover an ancient city buried beneath the ice, built by a civilization predating humanity. The horror is not only what they find, but what the ice has preserved, things that should not still exist, kept intact across geological time. Lovecraft understood that ice does not simply kill. It keeps, and what it keeps may not always be safe to uncover. Ice skating as a human activity is far older than the sport suggests. Archaeological evidence indicates that people in Scandinavia were fashioning skates from animal bones as far back as 4,000 years ago, not for sport but for practical travel across frozen lakes and marshes. Bone skates have been found across northern Europe, suggesting widespread independent adoption of the same basic technology wherever winters were cold and waterways froze solid. The transition from bone to iron blades occurred in the Netherlands during the 13th or 14th century. Iron allowed the skater to push off and generate propulsion rather than simply glide, transforming skating from utilitarian activity into leisure and sport. The Netherlands became the center of European skating culture, and canal skating, covering long distances across frozen waterways, developed into a tradition that continues today in years cold enough to freeze the canals solid. Competitive figure skating emerged in the 19th century, formalized in England and the United States. The first World Championship was held in 1896. Ice hockey codified its rules in Canada in the 1870s and spread rapidly. Both sports required artificial ice to grow beyond cold climate regions, and the development of mechanical rinks in the late 19th century allowed skating culture to reach climates where natural ice was never reliably available. Artificial snow followed a similar path. The first snowmaking machine was developed in the early 1950s at a New Hampshire ski resort, forcing water and water, compressed air through a nozzle to produce snow crystals. The technology spread rapidly and is now standard at resorts worldwide. Artificial snow is denser and icier than natural snow and requires specific conditions, but it has extended ski seasons and made winter sports accessible across a far wider range of climates. The industrial engineering of cold reaches further still. Blast freezing tunnels chill food products to minus 30 degrees in minutes, preserving cellular structure in ways slower freezing cannot. Cryotherapy chambers expose the body briefly to temperatures as low as minus 140 degrees, with claimed benefits for recovery and inflammation. Cold, managed and manufactured, now runs invisibly through much of modern life, from hospital corridors to supermarket supply chains. Ice has accompanied human civilization from its earliest moments, as threat, as resource, as wonder, and as tool. It carved the landscapes we live in, preserved the dead for us to study, and carried organic molecules across the solar system. It sits in the glass beside you and in the ice cores that hold 800,000 years of atmospheric memory. It is older than the continents in its current form, and younger than a single winter in its most fleeting. Ice has also shaped language in ways that go unnoticed. We describe cold relationships as icy, cold stares as glacial, cold silences as freezing. We break the ice to begin conversations and put things on ice to pause them. The metaphors are so embedded that their origin in actual cold has become invisible. Ice shaped the terrain, the climate, the food supply, and then, quietly, shaped the words we reach for when we want to describe distance, stillness, and the passage of difficult time. What makes ice worth a night of quiet attention is not any single fact about it. It is the accumulation, The realization that something this ordinary is also this strange. The hexagonal geometry of a snowflake, the blue inside a glacier, the ocean beneath Europa's crust, the frog that freezes and wakes. Ice is not just cold water. It is one of the great organizing forces of this planet and this solar system, hiding in plain sight. And now you know a little more of what it actually is.